Hello and welcome to the InterPlex. Horacio Corti is an Argentinian physical chemist, a full professor at the University of Buenos Aires, and a researcher and longtime member of Argentina's National Atomic Energy Commission. Corti has researched a wide range of condensed matter and material physics phenomena over his long and productive career, from membranes and nanoscale microscopy to applications of density functional theory and energy storage systems. Much of his recent research has been focused on lithium, both its extraction and isotopic separation, as well as its applications beyond batteries, especially within nuclear technologies. Our InterDialogue spanned a range of topics, though focused a good amount on the complex environmental, economic, and geopolitical landscape around the lithium supply chain, and how lithium has tremendous added value within present and future nuclear technologies. Thank you for being here with me, Horacio. It's very nice to see you again.
Thanks to you, Daniel.
All right, so before we get into some of your really fascinating research onto lithium and its applications for nuclear technologies, I'd like to ask you a bit more generally about Argentina and the sort of the status of nuclear energy and nuclear technologies in the country. Some of the history, you're a member of the National Atomic Energy Commission. So just a bit more context, like what exists in Argentina and what has been the development of nuclear technologies in the country?
Well, actually, Argentina is a nuclear country. The Atomic Energy Commission was created in 1950. That is 74 years old. And so far, we have developed a lot of technologies. Indeed, there is a company that is a spin-off of the Atomic National Energy Commission that is called INVAP. That is mixture company, state and public, that developed a nuclear reactor, research a nuclear reactor. Okay. And Argentina had exported several reactors to different countries all over the world. And also, INVAP and CONEA have constructed the Argentine nuclear reactors that run in different parts of the country, mainly for research purpose and only for the production of radiopharmaceuticals. Argentina is a country who in his energy matrix has about 9% of nuclear energy for the production of electricity. The first nuclear power reactor will start in operation in 1974. It was located 100 kilometers north from Buenos Aires. It's called Atucha 1. 8 years ago, the third nuclear reactor, Atucha 2, entered in operation. The Atucha 1 is the third 300 megawatt electric power reactor. Atucha 2 is 700 megawatt. And we have a second nuclear reactor, who is a Canadian technology. It's located in the Córdoba province, in the center of the country, and started in operation in 1986, I think. Is now very close to refitting, so it's going to produce electricity for mainly 25 years more in advance. So we have the 3 nuclear power reactors in operation, and the 4th one is in discussion because the former administration have a convenience with China to provide the 4th reactor, that there will be the first light water reactor The three we have are the CANDU and Germany power reactor that run with heavy water and natural uranium. But the Chinese reactor that is in discussion now because the new administration is reviewing all these issues. So we don't know if we have a four reactor from China or...
Sorry, these three reactors that are in existence, so they are pressurized water reactors, is that correct?
Yeah, pressurized water reactor that run with natural uranium or low enrichment uranium.
And
Argentina has also facilities to produce his own fuel, nuclear fuel, exporting uranium from abroad. We used to have uranium in the country, mines to extract uranium, but now the uranium came from abroad. And we have also a fabric to produce heavy water that it was closed for more than 10 years, and the former administration trying to renew it and start in operation because there is a lack of heavy water, not only in Argentina, but also in other countries that run with heavy water reactors.
Right, interesting. And
but all this is in doubt at the moment because due to the economic situation of the country, all the support for the nuclear industry and other industries and technology companies has been reviewing.
Yeah, it's been suspended. We'll get to that in a moment, the current situation. I want to ask also about some of the next generation reactors. Argentina was a pioneer in developing some of the small modular reactors, the CAREM 25.
Yes.
They're a participant in the Generation 4 Forum of Reactors. Can you talk a bit about that as well?
Actually, Argentina has his own designs of a small modular reactor. It's called CAREM. It's a project that has been run for several years for different reasons, and mainly economic reasons. And this project was stopped several times. Now, a prototype of this current reactor, that it will be a 32 megawatt reactor, is under construction in near Atucha 1, Atucha 2, in Zárate, Buenos Aires. And it's almost 80% complete, but it's in doubt if this reactor is going to be completed in the short term, all due to the economical issues.
Yeah,
but it's one of the most advanced designs of a small nuclear reactor. But, well, as you know, this kind of modular reactor, I mean, in development in different countries, in the States, in Europe, in China. So we have, very worried about that because we have the chance, we have in the past the chance to be the leaders in this kind of small modular reactor, but now there is a lot of competition all over the world.
Right. Maybe I can ask you just generally, what are some of the benefits of small modular reactors versus larger traditional reactor designs?
Well, they are intrinsically more safe than the higher power reactor. As the names indicate, they are modular, so you can put 2, 3, 4 modules ranging in between 30 and 50 megawatt. So you can afford the power you need according to the needs of the industry or the town where this kind of reactor are located. Mm-hmm. But intrinsically, they are safe. In particular, the current design has a security system, self-security system that make this the reactor really very, very, very safe in his run.
And how does that fit into
this is mainly the...
Yeah.
And also it can be used to produce, for instance, hydrogen. The industry that needs a lot of hydrogen, like the steel factories or the factory that produce fertilizer or methanol that need a lot of hydrogen, can produce hydrogen using nuclear energy. Of course, this is more sustainable than produce hydrogen using the reforming of natural gas.
Right.
So this is another application or possible application of these small reactors.
Right. Desalinization, I think, as well. Yeah, a lot of different applications for small modular reactors. And yeah, the nuclear hydrogen cogeneration is really fascinating too.
Yeah.
How does the CARAM design and small modular reactors in general fit into the Generation 4 reactor forum for advanced nuclear technologies, which Argentina, I believe, is a participant in, the G4 forum?
You mean the fourth generation of nuclear reactor?
Right, fourth generation.
Well, Argentina is not involved in the development of this kind of advanced nuclear reactor.
Okay.
We are more involved in the classical nuclear reactor, and this is small modular nuclear reactor, not in the fourth generation.
Okay, great.
We have an eye on that, especially in the sense of basic research, studying, for instance, the properties of sodium, liquid sodium at high temperature for sodium-cooled reactor.
Right.
And in our institution, there are groups that are studying this type of basic research or applied research, but we are not involved in the fourth generation of nuclear reactors.
For design, for construction.
Indeed.
Got it. What are some of the other research centers that participate in nuclear research in Argentina? So there's the one you mentioned. There's the commission, of course. There's the one in Aziza. What are some of the other centers that work on nuclear research?
The true one that I mentioned before, the Atomic Energy Commission, that since the creation till the middle 90s, where the nuclear power reactor was separated from the Atomic Energy Commission, and now they are in charge of the Nucleoeléctrica Argentina, that is a public company which has in charge the run of the 3 nuclear power reactors. In the past, there were intentions to privatize this nuclear reactor, but that was not possible. It's not easy to privatize nuclear reactor because, after get the lifetime, they had to be decommissioned, and this required a lot of time, a lot of efforts, a lot of labor and money. So there are not too much private people interested to be involved in the nuclear industry.
Makes sense. What about the Balsero Institutes out in Bariloche?
What about Balsero?
Balsero
is mainly institution for the formation of human resource. And the Instituto Balsero, they produce the nuclear engineers for the Atomic Energy Commission, for INVAP, and also theoretical physicists, for instance. In fact, one of the most important physicists and astrophysics nowadays, that is Dr. Malvaceda, is a graduate from the Balseiro Institute.
Right.
So we have here also in the Constituyentes Atomic Energy. The atomic energy has 3 atomic centers, one in Bariloche, where the Balseiro Institute is run, and other one in Buenos Aires, where I am working. We have here an institute called Jorge Sabato that is dedicated to the formation of a materials engineer.
Okay.
There is also another institute in the Third Atomic Center that is located in Ezeiza, very close to the international airport, where the Dan Benison Institute for people dedicated to nuclear security and radiochemistry.
Okay.
In these three institutes, the Atomic Energy Commission for people for the nuclear industry and also for the basic and applied research. But of course, the most important, the institute that has the better reputation is Instituto Balseiro at Bariloche.
Mm-hmm. Yeah, it's very recognized internationally for the people they produce.
Yeah.
You know, they're very impressive. So you
Yeah,
were
top quality.
top quality, yeah. So you were starting to talk about it. So what is going on in Argentina right now, in general, but especially in regards to the research being done on nuclear energy? What kind of cuts are happening? Are projects being suspended? I think it was just earlier this month that things were approved for, austerity cuts, I suppose, by the government and the Senate. So what is going on with all these different research projects, and where can things go from here, in your mind?
Well, during the later administration, there was a interest to development all the research and development in the area of the energy transition, the use of renewable energy like wind energy, solar. But actual administration cut all the funding so far, and also reduced the number of young research enter into the system. So they cut almost at half the fellowship for the graduating in different universities. So the thing is not going good. We are in danger that most of the young people go abroad, as happened in other situations, like during the last dictatorship, that many people, young people, and also training people go abroad, searching for better position or better condition for doing research.
Yeah, and specifically about the research projects and the construction projects regarding nuclear energy, have those been mostly paused or just stopped completely during the Milei
No, stopped
administration?
completely. Well, the new atomic energy president has is fighting for getting to get a higher budget for all the project that has been stopped. As for instance, the construction of the new research reactor in Ezeiza, that is the RA-10 reactor, is a reactor mainly dedicated to the production of radiopharmaceuticals, and also is going to provide the neutrons for the a new facility that is called the Argentine Laboratory, Neutron Beam National Argentine Laboratory, that will be, when this reactor is completed, will be a facility for research, basic and applied research in the area of materials, because as you probably know, the neutron techniques like scattering, neutron scattering, neutron reflectivity, neutron tomography are really useful for this kind of material research, not only for material research, also for soft matter, biological samples, and you can make a lot of things with neutron, and it's complementary of other laboratories in the region, like the Luz Synchrotron laboratory in Campinas in Brazil.
Okay.
So we have the hope that this laboratory will be a regional and also international facility, because it's going to be one of the most important laboratory in terms of the flux of neutrons. So we can in the future we can make very interesting experiments using neutrons, using the devices that are constructed right now in this laboratory, and also using devices that were donated by institutions in Switzerland and in Germany that closed down. This equipment had been donated to the Argentine neutron beam laboratory to work in the future with the neutrons produced by the RA-10 reactor.
Okay, so this
this is an important project in the area of science and technology in Argentina.
It's a big one, yeah. The RA-10 multi-purpose reactor, yeah. I had thought to ask you about that. So that is an example of a project that's currently been paused because of a lack of funding. That was in development and is now paused. So if the funding,
this reactor is almost 85% complete.
55%.
So it's supposed to be finished next year. Mm-hmm. If the funding came, that we are waiting to obtain this funding, in spite of the problems that all the science and technology sector is suffering here in Argentina.
All right, well, we can shift gears a little bit here and maybe start talking about this very interesting metal, lithium. And maybe we can start with its history, its cosmic history, because there are some interesting things that you've spoken about in terms of, where it came from with Big Bang nucleosynthesis and some of the primordial problems involved with its abundance. There's some mysteries around the abundance of lithium and its different isotopes in the universe. So maybe that's something you could talk about a little bit. It's it's something I find quite fascinating. And then we can start to talk a little bit more about lithium's applications here on Earth. But just its kind of cosmic history and abundance.
Lithium is known for the people because of the use in batteries, of course, and is part of the energy transition because batteries are the simple system that the humankind has to store energy. But lithium is also an element that is important for nuclear technology. Indeed, lithium-6, the lithium has two stable isotopes in nature. Lithium-7, that is in 92.5%, and the rest, about 10.5%, is lithium-6. Both isotopes has very different properties, physical properties. While lithium-7 is transferred to the neutrons, lithium-6 absorbs neutrons and produce tritium and helium plus energy, releasing a lot of energy. So the future fusion reactors that work by the fusion of deuterium and tritium need deuterium and tritium. Of course, deuterium is abundant in the earth because it's present in the water with a very, very low amount, but there is a lot of water, so we have enough deuterium for the fusion reactor. But tritium is not a hydrogen isotope that is in the nature. It's produced in the nuclear power station, but the amount that produced in the nuclear power station is not enough to sustain a fusion reactor like that is under construction in France. It's called the ITER reactor, that is a multinational reactor, a prototype of a fusion reactor. So lithium-6 will be the indirect fuel for the fusion reactor because by impacting neutrons on lithium-6 target, you can produce tritium. So this tritium is injected in the fusion reactor at very, very high temperature. Mm-hmm. over 100 millions of Kelvin. It will be the indirect fuel for the fusion reactor. Mm-hmm. Of course, there is not a certain about the successful of this fusion reactor. That in few years, the ITER project is planned to produce the first plasma. And if it's successful, I mean, if the fusion reactor produces more energy than the energy that consumed to produce the plasma, the next step is the demo reactor, that is a 1.5 gigawatt reactor, which will be the first commercial fusion reactor. That is the ultimate energy, because the fusion of deuterium and tritium doesn't produce any radioactive waste. So it's a completely clean energy. It's almost eternal, because you have a lot of deuterium, and having lithium, you have a lot of you have the possibility to produce tritium. So in my lab, we are working in the separation of the two lithium isotopes, with the aim to have enough lithium-6 to produce targets for the future nuclear fusion reactor. And also lithium-6 is used in several nuclear technologies that are using right now, like, for instance, the scintillator plates that are used for neutron eye machines has a small amount of lithium-6 of the order of grams, and so are the facilities, are the products that are required by the facilities that are dedicated to lithium tomography or neutron tomography or neutron reflectometry, and it's also used as a shield for neutrons and also for other radiation in nuclear centers like reactors. Well, of course, it has also military use, but in the past, lithium-6 was separated by the state and the later Soviet Union using a method that used huge amounts of mercury. Indeed, there is in the state this method of lithium isotope separation is forbidden. That was done during the 50s and 60s in Oak Ridge, and there was a huge contamination of all the water resources around Oak Ridge, and that are still being remediated. So we are trying to separate lithium isotope using sustainable method, using the insertion of lithium into metals or into oxides, or absorbing lithium into different kinds of absorbents like aluminum hydroxide, etc. So we are trying to perform this isotopic separation using clean method, clean and sustainable method. And they add value to lithium compared with the price of, for instance, the lithium carbonate. The lithium carbonate that Argentina produces right now, Argentina is the fourth producer of lithium in the world. 1 kilogram of lithium carbonate, battery grade, it costs $20 per kilogram. And 1 kilogram of lithium-6, when used, for instance, in nuclear sensor or a scintillator plates, it costs more than $4,500 per kilogram, $45,000 per kilogram. So the difference in add value is enormous when you use lithium for nuclear technology, and the amount that you require is much smaller than the amount required for producing batteries.
Okay, well, you're mentioning a lot of different things that are important, so I'd like to try to break down some of them, if that's okay. Going back to the fusion reactors, from what I understand, you're describing for the lithium six, it's a neutron capture blanket around the tokamak. Is that right? The plasma, which then helps to generate the tritium that then is used as a fuel for the fusion reactor. Okay.
Along with the deuterium, of course.
Along with the deuterium, right, which is more abundant in nature. So, how enriched does the lithium six need to be to form that blanket?
It's no more than 90%. 90%, between 19 and 95% is okay for the use as a blanket.
And does this work in some of the other fusion designs, like laser confinement and things like that? Is lithium six useful, or it's only useful for the tokamak design?
Sorry?
Is the lithium six blanket useful for other proposed fusion designs like laser confinement, or is it just for the tokamak?
No, this is only for the tokamak design. And the laser fusion, I think, is an early stage of development.
Right.
I don't know if they use. It's only. I have been only proved at the lab scale, so I suppose that the amount of tritium is very short, and they can be provided by. The tritium produced released in the light water reactor. But I'm not familiar indeed with the laser fusion. So I have read some reports from especially from laboratories from the United States, but I'm not familiar with the details of this
Lawrence Livermore
method.
Yeah, the Lawrence Livermore laboratory, I think, is the one that's most advanced. Yeah, so that was a question in terms of lithium 6 and its applications there. You mentioned, well, I'm a little bit personal. I think I had mentioned to you that I grew up the first years of my life in Oak Ridge. So this, what is it, the Colex method for using mercury to separate?
The Colex method is the method used for the Soviet Union and the United States during the Cold War. And it's a simple exchange between lithium hydroxide in aqueous solution and in mercury. The lithium 6 preferred to be into the mercury, forming an amalgam. And well, this is the method that has the best separation coefficient. It's almost double than the other methods. For instance, the method we are trying. But the problem is that you need a lot of mercury.
Right.
And of course, if you produce this in enough, I think that in Oak Ridge during the Cold War were used 9,000 tons of mercury, and around 500 tons were lost. They were found in the rivers, in the lakes, all over the Tennessee.
So how much damage?
When I visit this Oak Ridge National Laboratory in 93, I think, most of the budget of the Oak Ridge National Laboratory was dedicated to the mercury remediation.
That's terrible. How much damage did I do to myself by swimming in the rivers and lakes of Oak Ridge when I was a little kid?
Oh, my damage, I don't know.
I'll have to look into it.
But of course, all the mercury was found mainly in the sediments, and probably also in fishes and all the fauna in the region, aquatic fauna.
Right. Yeah, it's pretty scary stuff. It's good that they're not doing that.
But what is, really worry about is that China and Russia, that are the main producer of lithium 6 right now, are using the Colex method or variation of the Colex method. So they are using a lot of mercury.
Yeah, that's pretty crazy. All right. Well, and you talk about the added value too. So maybe to tie a couple of things together. So by appreciating the value that lithium provides to these advanced technologies, nuclear energy, scintillators, imaging for neutrons, I think what you're proposing and what I've read in your research is that this can also help to incentivize preserving the reserves of Argentina's lithium, not to just exploit it for batteries and things like that. Is
Yeah,
that what you're proposing here more than anything to appreciate the added value that lithium provides and to make sure to not just mine it all and sell it all off for batteries?
I'm trying to convince the authorities of especially the authority of the National Atomic Energy Commission, that lithium is an strategic element for nuclear technology, and as a nuclear strategic element should be in such a way it should be protected. For instance, in Chile, the Atomic Energy Commission, there exists an Atomic Energy Commission in Chile, in spite of the fact that Chile is not a nuclear country. They have no nuclear reactor, they have no nuclear activities, basic research in nuclear technology. But the Chilean Atomic Energy Commission is consulted by the government when the mining extraction companies try to increase the importation of lithium carbonate for battery factories. That means they consider the lithium a strategic element. They try to maintain some reserves in case that lithium in the future could become an indirect nuclear fuel for fusion reactor. That doesn't happen in Argentina, in spite of the fact that Argentina is a nuclear country. And this is really a contradiction. This is surprising. The problem is that our laws, all the lithium extraction regulation are in hands of the province, not from the central government. And this is established by the Constitution. And despite that there is a law where the Atomic Energy Commission stands a responsibility for all the feasible and feasible elements in the country. The Constitution has a high level of power, so the province dominate the lithium policy, and the policy is to export as much as lithium as possible. And if you consider the projected expansion of electric vehicles in the world from now to the end of this decade, if you consider that increase in the number of electric vehicles, that will be 200 million at the end of this decade, this requires almost half of the lithium in the lithium triangle. That is the lithium that is in Argentina, Bolivia, and Chile. So
That's a lot, yeah.
in few years, we can get out of these resources.
Yeah.
And on contrary, if you use this lithium in the future as a fuel for fusion reactor, you spend very, very low. That means to run the fusion reactor like the demo, that will be a 1.5 gigawatt reactor for 1 year, you need about the amount of lithium that use 200 electric cars like Tesla. To have an idea of the small amount of lithium that require the fusion reactor.
Yep.
To
Absolutely.
produce energy.
There's a real risk, and there's a lot of there's a lot of news and geopolitics going on about.
What I say that we can export lithium carbonate for batteries, but we have to be careful to keep some amount of lithium for future fusion reactors.
Yeah, and there seems to be a strong push of the current administration, the Milei administration, to be selling off a lot of the lithium reserves of Argentina. There's been a lot of established connection with some of the business people, Elon Musk and others, that are looking to exploit some of the lithium reserves. So, if I understand correctly, what you're proposing is to make sure to preserve at least a portion of Argentina's lithium reserves for technologies that where it's much more efficient and much more valuable.
Yeah, and there are under development. I mean, there is not a dream for the next century. It's
Right.
for maybe 10, 20 years. So anyway, 90% of the lithium is in the seawater. So if somebody developed the method to extract economically lithium from the seawater, the problem is solved, because I mean, the amount of lithium in brines and rocks are negligible related with the amount of lithium in the seawater. The problem is that the concentration of lithium in the seawater is so low that the extraction method is very expensive and has not been optimized.
There's so many things.
But there is a lot of people working.
Yeah,
and of course, also, the lithium in the battery is not consumed, so you can recycle. There is a lot of research in the world related with the recycling of the cobalt, copper, and lithium in the battery.
Right.
And really, the incidence of lithium in the cost of the battery is no more than 4 to 10%, depending on the type of battery. Okay. So lithium is probably not the main component of the battery in terms of cost.
Just as a kind of side thing, I remember reading an article about nuclear desalinization, and the brine that's produced from nuclear from that process can potentially be mined for lithium. Is that something that you're familiar with? I just thought to ask you about it. So, as like future projecting of other added value, I suppose, of nuclear technologies, nuclear desalinization also produces a brine that might be more rich in lithium than seawater. Is that something that has some potential for mining lithium?
I used to nuclear energy for desalination of water.
And then the brine that's produced from that is richer in lithium than, of course, just natural seawater.
Yeah. Yeah, I'm not quite familiar with this.
I read an article about it some time back. I was just curious to ask you. All right, I want to go back to some other things that you've mentioned here. Yep.
Yeah. Now, the main goal of the companies that extract lithium in the brines in Chile and Argentina, Bolivia doesn't extract lithium yet, is to try to go from the evaporative method that takes 12 till 18 months to produce lithium, because you concentrate the lithium in the brine just by solar evaporation, by using direct method. For instance, electrochemical or absorption method, or ion exchange method using ion exchange membranes. So if these methods are developed in the next year, and probably they will be available in the next year, the extraction of lithium in the lithium triangle in Chile, Bolivia, and Argentina will be more rapid than is now, because now it's restricted by the evaporative method. You cannot extract lithium with the method waiting less than 1 year.
Yeah.
So, but with direct method, you can do it. You can do it in very short times.
And what are some of the drawbacks of that method?
The technology will be more clean than the laboratory method that require a lot of fresh water. But the research is going down more rapidly if these direct methods are applied.
Oh, okay, that's good to know, because I was going to ask you about the different methods. There's electrochemical, which is You put me in contact before with Ernesto Calvo, who works on electrochemical techniques for separation.
She is working in this method, and there is also people in Jujuy, Victoria Flexer in the CIDMEJU, that is Institute of dedicated to extraction and application of lithium and other energies, are using this electrochemical and electrodialysis method for the separation of lithium from the brine.
Right, exactly. So, but if those are developed, if those are more successful, then you're saying the reserves could be depleted more quickly as well. So it's kind of a double-edged sword. There's this other technique, more advanced technique. What is it called? Alvis, maybe, using lasers and the difference in ionization energies to separate lithium-6 and lithium-7.
Yeah, well, actually, our project has two parts. One part is the electrochemical separation. That is what I'm involved in. And the other method that is development in the Atomic Energy Center in Bariloche use laser. There is a very, very small, ridiculous small difference of energy of ionization. And it means you can extract an electron from the lithium, but the energy you need to extract an electron and to convert the lithium in a lithium ion is different for lithium-6 than for lithium-7.
Right.
The difference is very, very, very small. But if you can use dyed laser that are tunable laser, you can adjust the energy of the photons in order to ionize one of the isotopes, for instance, lithium-6, without ionizing lithium-7. So you can separate. After that, you can separate very easily the ionized lithium from the non-ionized lithium just by using electric fields. And in that case, the separation is complete, or almost 100% complete, because all the ionized isotope is separated and the other is not, goes.
That's an alternative to the Colex method, correct?
Yeah. But the problem is that the amount of lithium you can separate is much smaller.
Yeah.
You need, and means to produce a few grams of lithium-6 using this ABLIS technique, you need very, very powerful laser. So the cost of capital to do that is very important. For instance, our project was initially have a budget of 300,000 euros to buy 2 lasers to produce this kind of selective ionization. With these lasers, we could produce small amounts of lithium-6 of the order of grains by month.
I understand.
So, in order to escalate this, to produce higher amounts of lithium, you need really a very big capital investment.
Yep, makes sense. One thing we haven't spoken about much, you're talking about the added value of lithium-6 and lithium-6 enrichment. Lithium-7, enriched lithium-7 also has a lot of applications, including for the fission reactors. And
lithium-7 has an application as in the form of lithium hydroxide. Is used as alkalinizing agent to prevent corrosion in most of the water and heavy water power nuclear reactor. And you have to use lithium-7 with a very high isotopic enrichment, more than 99.9.
Yep.
Because, as I mentioned at the beginning of this talk, lithium-7 is transparent to the neutrons. That means that it doesn't produce any reaction that produce radioactive products. If you use another kind of alkaline agents, to increase the pH of the primary circuit in order to maintain the corrosion as low as possible. For instance, if you use sodium, you produce a lot of sodium isotopes that are radioactive and increase the amount of radiation in the reactor. So this increase the radiation field and make the operation of the maintenance of the reactor more difficult. So in this kind of reactor, it's important to use lithium 7 hydroxide as alkaline reactor. But the amount of lithium hydroxide enriched in lithium 7 is very small. It's about 200 or 300 kilograms per year.
Oh, that's
and the amount of lithium and the amount of power nuclear reactor in the world is not so big. It will be at the order of 200 or 300. So
interesting.
Maybe in the future in China we have probably most of this kind of reactor. So with a production of few tons of lithium 7 per year, it's enough to maintain this the stock of lithium 7 to use for this application.
That's good to know.
But it's the only one.
Again, going back to some of the advanced nuclear designs and maybe molten salt reactors, including potentially thorium reactors. I think they propose to use lithium, beryllium,
the molten salt. If successful, they will be used several tons of lithium 7.
Right, and that's for lithium, beryllium fluoride salts. Is that right? And does that include thorium reactor proposals, or is that just for?
Pardon, sorry, I didn't.
So talking about molten salt reactor designs. Lithium fluoride, lithium beryllium salts. Could that also be used for thorium reactors? They use molten salt or
fluoride.
Just uranium?
It's lithium fluoride.
Yep.
Mixed with uranium. Yeah.
With uranium. Yeah. I when I read some about thorium reactor designs, I think they proposed to use this FLIBE salt, which included beryllium as well. I wasn't clear if that was lithium 7 or not, but I guess what you're saying is that all molten salt reactors will use a substantial amount of lithium 7. Is that right?
Of lithium 7, yeah. That will be in the future will be the main requirement for lithium 7, much higher than the use of lithium 7 hydroxide for as alkaline agent for PWR.
So is that another substantial added value for lithium? Molten salt?
Yeah.
What about
that's it. Yeah.
What about for energy
but
storage?
In that the problem is that the lithium 7 for this application should be better than 99.95%. So it's much difficult to get this enrichment in lithium 7 that to reach 90% in lithium 6.
Okay, interesting. Using the same methods, whether it's the collox or electrochemical.
Of course, when you enrich lithium 7, for instance, by electrochemical method, inserting lithium 6 into metals or oxide, in this solution you have an enrichment solution of lithium 7. So you have in the head, you have a lithium 6 enrichment, and in the waist you have a lithium 7 enrichment. Okay. And the process is, of course, it's a cascade process that you need a very, very high number of stages to produce the enrichment degree you require. Okay.
Got it. Yeah. So what about for energy storage systems? Molten salts for energy storage. And I think you published a paper of, water and salt for energy storage. Is lithium 7 important for those as well? Molten salt energy storage?
No, I don't. Lithium chloride or lithium bromide is used as a concentrate solution, as a system for storage energy, heat, but basically, doesn't require any lithium enrichment.
Got it.
You can use natural lithium for that case. Oh. In that case,
is that?
And using the water in salt, I mean solutions, very concentrated solution of lithium salts in water, in order to replace in this process method of enrichment. Is usually this method usually use lithium salts dissolved in organic solvents, because the potential, the electric potential you need to reduce the lithium is very high. It's of the order of between 3 and 4 volts. And at this potential, the water decomposes. I mean, if you try to electrolyze to reduce lithium from an aqueous solution, when you reach 2 volts approximately, you decompose water in hydrogen and oxygen instead of reducing lithium. So to avoid that, people use organic solvents. But if you use very concentrated lithium salts in water, most of the water in this solution are forming part of the hydration layer of the lithium ions. So this water doesn't split into hydrogen and oxygen. Okay. So you can use the same electrochemical method using aqueous solution. And this is very important. And we are working with this type of electrolyte. That means that are less expensive materials, and also more clean, because otherwise in the process you have to discard this organic solvent that in some cases are dangerous products.
Got it. And is this another important possible future added value product for lithium, something that should be considered, water and salt solutions?
Yeah, but the idea of use this water in salt solution came from basic research, where some people are proposing this water in salt solution as electrolyte for lithium batteries, for lithium ion or lithium oxygen batteries, in order to replace organic solvent by aqueous solvents. So probably in the future, lithium batteries will run with using this water lithium solution.
Okay, so it might be part of the same supply chain, I suppose, of exploiting lithium for batteries. Got it. So something I had started asking about before, I think it's very interesting to hear from you, and for anybody listening to this, just more about lithium in its natural place in the universe and here on Earth. Maybe it's something that you could expand upon a bit, like where does lithium come from? I think there are some interesting mysteries in cosmology regarding lithium, like in its abundance and its different isotopes, lithium-7 versus lithium-6. And then just a bit more context about where lithium is found on Earth and in what forms is it found. You mentioned the ocean, but there's salt flats and rocks, but I think it's just interesting to have that context of what lithium is outside of human use as well.
You mean outside of the Earth?
Outside of the Earth, and then on the Earth outside of human exploitation of it. What is lithium?
Yeah,
and why is it so interesting?
When I started to work in lithium was discovered 200 years ago by the Swedish chemist, and it was the first alkali metal discovered into a rock. Sodium and potassium were discovered before lithium, but were discovered in organic material. But lithium was the first alkali metal discovered in minerals. Okay. But it's important to recall that lithium was formed during the first seconds of the universe after the Big Bang. Yep. The first atomic nucleus that were formed after the Big Bang were hydrogen, deuterium, and tritium. In one of my talks, I like to speak about the fact that one of the experimental fails of the Big Bang theory is that the actual theory doesn't predict the relative abundance of lithium-6 and lithium-7 in the universe, mm-hmm. in the galaxies. Right. This is there are just recent papers, no more than 5-10 years ago, where astrophysicists are looking for an error in the experiments, because everybody assumed that the Big Bang theory, the nucleosynthesis theory is okay, but still the amount of lithium-6 and lithium-7 detected in the space, in the interstellar space, doesn't match the prediction of the nucleosynthesis theory, I mean the Big Bang theory. Mm-hmm. That is interesting. Right. But most of the lithium in the Earth, I think that lithium in abundance is in the position 35, 37. It's not an abundant element in the Earth, but 99% of the lithium is in the seawater. Mm-hmm. There is a small amount in brines and other amounts in rocks, mainly in Australia. That is the first lithium producer, and they take the lithium from the rocks. There is a lot of lithium, of course, going around the universe, but
when you say
the abundance doesn't match the Big Bang theory.
Okay, that's fascinating, and my background's more in cosmology and gravitation, so that really piques my interest.
Yeah.
But so when you talk about brines, that's the salt flats, that's the lithium triangle. That's when you mention brines, that's where most of the lithium is concentrated in the lithium triangle through salt.
The brines are rich in sodium chloride, mm-hmm. sodium potassium chloride. They have also sulfate and borate. And lithium lithium chloride is the minor component. Okay. In the lithium triangle, Chile, Bolivia, and Argentina, the amount of lithium chloride in the brines range between 200 and 400 ppm. Mm-hmm. So it's relatively a small amount of lithium in the brines. Mm-hmm. That's the reason why the evaporation method is so long. I mean, it takes a lot of time to concentrate the solution and precipitate sodium, mainly sodium and magnesium and potassium, and finally to get rich concentrated, relativity concentrate lithium solution that is finally precipitated with lithium carbonate.
How much water? How much water is used for that process, the evaporation process, to produce?
A lot.
Yeah.
Well, I don't remember exactly. I think that is in my paper that I sent to you, but it's about 5 tons of water per kilogram of lithium carbonate.
It's crazy.
Of fresh water.
Fresh water in
a desert region. You evaporate a lot.
Yeah.
Then between 12 and 20 more water from the brines, but this is not potable water. But you need about 5 tons of fresh water per kilogram of lithium carbonate that you produce.
And where does this water come from? Where does the water come from?
From the subterranean waters.
Because it's a desert. It's basically a desert.
Groundwater. Yeah. So this is a more important environmental impact of the lithium extraction.
Right.
The point that the places where these brines are located, there are not too much population. There are not too much people,
Right.
but the people who live there instead is going to suffer the lack of fresh water in the future,
Yep.
in the next future.
Yeah, absolutely. Right. So
So the main concern related with the lithium extraction in this region of South America is what happened with the freshwater reservoirs.
yep, very important. All right. So let's shift again here. You wrote.
That's the reason why the direct method is important, because it's supposed to reduce very strongly the amount of water you need to produce 1 kilogram of lithium carbonate.
Yeah, absolutely. For the water use, the efficiency, the speed. Yeah. Another thing you've researched and written about is hydrogen and lithium as part of a clean energy transition. And I think that lends itself to combining some of these different points. But maybe you can speak more generally about, we're speaking a lot about lithium, maybe you can speak a bit about hydrogen as well, but how these fit into more policy. And I read your article about the proton exchange membrane, electrolyzers for fuel cells, and yeah, just a lot of interesting possibilities for combining some of these as alternatives to batteries as well, using hydrogen fuel cells and as a form of storage. And then the production of green hydrogen, but also the production of hydrogen through nuclear energy. There just seems to be a few different components that can be tied together here. So maybe you can comment on that a bit.
Yeah. Well, about 20 years ago, I started to study the materials for fuel cells. Fuel cells are, let's say, that are like the inverse the inverse process that in electrolyzer. In electrolyzer, the input is water. Mm-hmm. You apply an electric potential. That means you apply electric energy and separate water in hydrogen and oxygen. Mm-hmm. The fuel cell is essentially the inverse process. You inject hydrogen through a cathode, oxygen through an anode. In this electrodes, it happened the oxidation of hydrogen to protons, and in the anode, the reduction of oxygen to oxidized. So you produce water and energy. And there are different types of fuel cell. I started to study the low temperature fuel cells that are called PEM fuel cell by polymer electrolyte membranes. Okay. It means that the current, the electric current between the electrodes is transported through proton ions in the membrane. In a membrane that has a matrix with negative charge that are fixed charge, like group sulfonate group, mm-hmm. and the hydrogen are mobile. So you can conduct the current through the fuel cell by transporting hydrogen from the cathode to the anode. During several years, we have been working in the new catalyst, trying to replace platinum. That is, of course, very expensive and not so abundant in the earth. Mm-hmm. So we have tried to use catalysts, replacing platinum partially by other metal like nickel or ruthenium. We also tried to make fuel cells that were not with hydrogen but with methanol, and you can use methanol as fuel for this fuel cell. We also developed membranes to work at higher temperatures, because the commercial proton exchange membrane fuel cell work with Nafium, that is a polymer produced by DuPont. Okay. The patent is expired, so there are other producer of this ion exchange membrane in Japan and Germany, etc. But the problem with this membrane is that when you go try to run this fuel cell at temperature higher than 90 degrees C, it became dehydrated, lost a lot of water, and the resistance of the electrical resistance of the membrane increased, and of course the efficiency of the fuel cells decreased also. So we are trying to produce higher, better ion exchange membrane based on other type of polymers like polybenzoyimidazoles that could run at a little bit higher temperatures, up to 150 degrees C.
Okay.
So the efficiency of the electron reaction increased, and you can produce energy with more energy using running the cells at high temperature. There are also people here in the Atomic Energy Commission working in high temperature fuel cell that use as electrolyte ceramic with oxygen vacancies that conduct the electricity through this oxygen vacancy. This fuel cell run at temperatures around 600 or 700 degrees C, and of course they have a better efficiency because at that high temperature you can not only reduce oxidized hydrogen, but you can also oxidize natural gas, methane. Mm-hmm. So you can use different kinds of fuels, not only hydrogen. Right. And of course, all these systems can run in inverse words. It means the same material that are using as electrolyte for fuel cell can be using as electrolyte for electrolyzer. Okay. So you can construct high temperature electrolyzer using the same electrolyte, solid electrolyte, use it in high temperature fuel cell. Or you can use PEN electrolytes using this membrane exchange, proton membrane exchange. And that's what we also try to develop here. And electrolytes are the main device in order to produce hydrogen energy using solar energy or wind energy, because we have a lot of wind in Patagonia. We have very insolation regions in the north of the country, mm-hmm. near where the lithium brines are located. Mm-hmm. So we can produce a lot of electricity using wind and solar power, but you need to storage that energy, because in that region there are not too much people living. So you have you need a transmission line, or you need to store that energy. And the way to store that energy is to produce hydrogen, for instance. You can produce hydrogen using electrolyzer when the sun is shining, or when the wind is blowing, and you can storage as hydrogen. Or you can store it also as this hydrogen, you can convert it in ammonia, and you can export green hydrogen as pressurized hydrogen, or you can export hydrogen as liquid ammonia. Yep. That is much better than transport gaseous hydrogen.
Sure, it's not
in Argentina, there had been a lot of projects. The last one, it was a project by an Australian company. I don't remember the name now, but they had proposed 3 or 4 years ago to install a wind park in Patagonia, in Santa Cruz, in Chubut, in the Patagonian province, in the south of the country, to produce hydrogen green to export to Australia and also to Europa. But this project has not been started yet. But Chile has 2 projects, one in the north using solar power, and one in the south, in the Chilean Patagonia, using wind. And there are American and Italian companies involved in this project. And Chile is in condition to export, for instance, this hydrogen, green hydrogen, to Japan through the Pacific. They have the advantage to export hydrogen to Japan directly because they have the ports on the Pacific side. But there are also German companies interested to produce green hydrogen in Argentina. There is a recent study from the Fraunhofer University Institute that make an economic estimation of the cost of the hydrogen, green hydrogen produced in Argentina using wind power, and they estimate that the cost will be around between $4 and $5 per kilogram. And this is a cost that the German and Korean and Japan could pay to meet the requirements for green energy in that country.
Right.
International target, especially this target from the EPRI in the state, is the call 111, $1 per 1 kilogram of hydrogen in 1 decade.
Yeah.
But we are still far from that target. The cost of the hydrogen, the black hydrogen that is produced by reforming natural gas, is of the order of $1. The idea is to produce green hydrogen at the same cost, $1 per kilogram, at the end of this decade.
And something always very, very interesting are these hybrid systems. And since we were speaking about nuclear energy before and touched on the nuclear hydrogen cogeneration, and also there's other uses of some of the advanced nuclear reactor designs, again, desalination.
Yeah.
So the hybrid systems can then have the nuclear and the renewables integrated together, and there can be the production of hydrogen as well for storage. So how do you see the role of nuclear energy in the production of clean hydrogen? Maybe it won't be called green hydrogen, but a clean, sustainable hydrogen. What do you see the role of nuclear energy in hydrogen cogeneration?
The hydrogen produced using nuclear energy is called pink hydrogen. Okay. There was a meeting some years ago in the International Agency for Atomic Energy in Vienna. I attended that, and they produced a report on the cost of the use of nuclear energy to produce hydrogen, and still is very, very high. Why? Because the nuclear power reactors are base powers. I mean, they mainly work at 100%. There are not peaks hour or the reactor works at 100% of its power, because it's not possible to cycling. To cycling the power attending to the demand. So the idea of the use of nuclear energy to produce hydrogen, pink hydrogen, is using this type of small nuclear reactor dedicated exclusively to the production of hydrogen, or using the advanced high temperature fourth generation nuclear reactor that works at high temperature to produce hydrogen using thermodynamic cycles, using, for instance, sulfur dioxide and iodine at split water at temperatures around between 400 and 700 degrees C. That is possible to cogenerate hydrogen and using this type of reactor, but not using directly the electric energy to electrolyze water, but the thermal energy to produce hydrogen by splitting water at lower temperature.
The heat, yeah, using the heat to then thermonuclear reactions. What do you know some of the fourth generation designs that operate at a high enough temperature for that to be feasible?
No, I'm not familiar with that. Could say nothing about that because I have not the idea what is going on in this area.
Yeah, no, but it's quite interesting and
yeah, it is.
yeah.
In Canada, there was in Ontario Tech University. I have a college working there, and in this university there was a lot of effort to develop thermodynamic cycles for splitting water,
Yeah.
thinking in the future advanced water reactor, high temperature water reactor.
Yep, exactly. Yeah.
Also critical water reactor.
Yep.
They have enough temperature to split water. Yeah.
Exactly. Yeah, fascinating. What are some of the other materials that lithium can be used in relation to energy technologies, such as wind turbines? How can lithium also be part of the clean energy transition, essentially, is my question.
Well, of course, as a component of battery, advanced battery with higher energy density.
Right.
So you can store more energy in less weight or less volume. Lithium is also used in the fabrication of high alloys, like that used in the aeronautical field. Well, I think that's basically the role of lithium in the energy transition. When I start to make research in this area of hydrogen and lithium, I read a book about the hydrogen economy, and this author, Smith Road, a German author, specialist in hydrogen, say that fuels doesn't compete. They would compete are technology. So the better technologies will be will have a biggest role in the energy transition. So, for instance, in the case of the electromobility, of course, the electric vehicles are mainly drive with lithium batteries or nickel hydrogen batteries. Mm-hmm. But in Japan, there are also vehicles drive by fuel cell. Toyota has a Toyota Mirai, and in Japan there are a lot of hydrogen spender where you can charge hydrogen in your Toyota Mirai and run more than 500 or 600 kilometers. That for a small country like Japan is okay.
That's great. Yeah.
So I don't know. We have probably in the future we have to live with several kind of electric vehicles driving with hydrogen, like driving with batteries. Mm-hmm. Probably there are also a lot of research trying to introduce sodium batteries that have lower power energy, but sodium is much more abundant than lithium, so you have not a restriction about the use of sodium. And in China, there are important advances in the development of sodium batteries. So in the future, you will have a cocktail of batteries and alternative fuels for vehicles.
Well, you mentioned Japan, Argentina, Latin America in general, even the United States. How much potential do you see for the hydrogen economy? You say it's based on what will be the best technologies. It also seems to be based on how hydrogen can be produced and what other technologies.
Argentina and Chile are mainly have been indicated as green hydrogen exporters. The internal market for hydrogen is small in Argentina, but we have chance because we have the resource to be exporter for the countries that are seen as green hydrogen consumer because of the regulation, Germany,
right.
Japan, and other countries in the North Hemisphere that require hydrogen, green hydrogen, to fulfill its decarbonization targets. So Argentina and Chile mainly are hydrogen producers.
But if they move away from fossil fuels and internal combustion engines, you think Argentina, Chile, Brazil, for example, would move more towards electric vehicles and lithium-ion batteries, or is there the potential to introduce fuel cells in these countries?
Well, actually, in Brazil, they used to mix gasoline with methanol.
Yeah.
And they are still doing that. In Argentina, we have a lot of vehicles, especially taxis and buses that run with compressed natural gas.
Right.
There was some studies to estimate the possibility, to see the possibility of a mix 10 or 15% of hydrogen into the compressed natural gas. This is understudied, but it will be a chance. The problem is that sometimes you need to make some modification in the injection system of the vehicles. But it's possible theoretically to use 10, no more than 15% of hydrogen mixed with the natural gas. And Argentina has the infrastructure to, we have a compressed natural gas all over the country. So you can really safely introduce 10% of hydrogen. That will be very nice for the country, provided that you can produce this hydrogen by sustainable method, of course, not by reforming.
Yeah, exactly. Very interesting. All right. Well, maybe we can close this out just with a more general. Going through your research, a few different things are mentioned in terms of geopolitics and the way that plays a role in a lot of what we're talking about, whether it's international treaties in terms of the energy transition, or the war in Ukraine, which has to do with the enrichment of lithium, for example, and what might be available because Russia is one of the major producers of that. And then, of course, just the situation in a place like Argentina and the political landscape. So I guess I just want to open this up to see how you think it's possible to communicate to policymakers the importance of this kind of research and how to prioritize added value of things like lithium for nuclear technologies and to preserving lithium reserves in a place like Argentina. How does geopolitics come into play in something like this? How can these things be best communicated? Their importance to those that make decisions, essentially, for the public.
Well, this is a very complicated question because especially in this moment and in our country, there are a lot of changes in the geopolitical situation. In the former administration, we were more aligned with with people who were interested in to have deals with China to provide a nuclear power station, with Japan and Korea to export green hydrogen. But now, with the new administration, I think that these things are changing. But we don't know in which direction. There is a change of geopolitical interest during the last month. So the situation is uncertain. It's uncertain not only for people who made research and trying to make research and technology in Argentina, because we are not sure to have funds in the near future, but also in the energetic policy. We have a lot of gas and oil in Vaca Muerta, in Neuquén. Our main energy company, that is YPF, Yacimientos Petrolíferos Fiscales, YPF, it's very interesting to get investment to produce more gas and shale oil to export, and in order to obtain dollars to benefit our damaged economy. So I think that all the effort that during the last years has been made in order to try to introduce research and projects in energy transition are going to be delayed for maybe some years. The main effort from the government is put in trying to get investment for these shale gas and shale oil reservoirs. Indeed, recently the Senate has approved a law where there are very important tax benefits for the companies that invest a huge amount of capitals to this kind of extractive activities, not only for gas and oil, but also for lithium, copper, etc.
Right.
So I think that this is, we are in the transition age now in our country. I don't think that the emphasis is put on energy transition or the production of green energy or exporting, but just to exploit our gas, lithium, oil reservoirs to get money as quickly as possible.
Oh, that's concerning and disappointing with so many advances that were made over the past decades. So sad to hear, but hopefully these projects will be able to be invested in and reactivated in the near future, because there's a lot of potential.
Thank you for joining us for this InterDialogue. You can subscribe to be notified of future episodes and by following us on our social media channels at the InterPlex. Visit our website, theinterplex.org, for more interdisciplinary and intercultural content and to join our growing collaborative community.